Now we look at the concept of variance for a random variable. So the way it's defined looks a bit weird, but we'll make sense of this as we go through. The variance of a random variable x we write is var of x, and this is essentially from x we take the mean away, we square it, and then we find the expected value or the mean of that. In other words, we're taking a look at the mean of x minus its mean. We also use the symbol sigma squared x for variance of x, and the standard deviation is the square root of variance, something that may be familiar to you. So standard deviation is the square root of variance. An example here will clarify how this works. So here is my random variable x. You can work out the mean here is equal to 1. If I look at e of x minus x squared, mean of squared, which is the variance of x, remember what I'm going to do here is, all I'm going to do is, from x I subtract the mean and multiply the probability. That's how I find the mean of things. Whatever I find the mean of, I take the value of this and multiply the probability. So it's actually negative 1 minus 1 squared times 0.1 the probability. Right? So remember all this happening is, from each of those values I'll take off a minus 1 here. In other words, the mean is minus 1. So from negative 1 I subtracted the mean, squared times the probability, and then 0 minus the mean, squared times the probability, then 1 minus the mean, squared times the probability, and finally 2 minus the mean, squared times the probability. So if I do the calculations here, negative 1 minus 1 is negative 2 squared is 4, this gives me 0.4. This is negative 1 squared, that gives me 1, 1 times 0.2 gives me 0.2. That's 0. And 2 minus 1 is 1, and 1 squared gives me 1 times 0.4 is 0.4. This adds up to be 1. And that's how simple it is to work out a variance. Properties of variance. Well, variances can't be negative, so they're always bigger than or equal to 0. And there's a simpler formula for working out variance. It's the mean of x squared minus the mean of x whole squared. And we'll see how this works in a little while. And also variance of ax plus b is a squared variance of x. So the b makes no difference. So we'll see how this works later on, and there's a proof for this afterwards. You can look at it if you wish. But if I take a look at scaling this and shifting it, the shift doesn't affect the variance. But the scale works is a squared here. Now, as far as variance and standard deviation are concerned, they both measure spread. Tells you how large the range of values the distribution of the random variable takes here, and how concentrated is the probability distribution here. So a random variable with only a few values that lie close to each other with high probability will have a low variance, and a distribution with a large number of widely spread values with not too low probability values, very well spread out essentially, will have a large variance. And a distribution with large widely spread values, well, the probability is concentrated in a very narrow region. So it's not just the large why the number of the value itself of the random variable, but where the probabilities are. So a large number of values, the probabilities all together concentrated somewhere else, can also lead to a small variance. And while variance and standard deviation both measure spread, standard deviation is a little better because it's in the same unit. So if you look at variance, it's squared. So I'm looking at something like the weight of a person in kilograms. Variance is in kilograms squared, whereas standard deviation is in kilograms back in the same units as the original measurements. So standard deviation is a better measure of spread. And variance, however, has its own importance, as we'll see later on. An example over here. Grizzly bear litter sizes are between 1 and 5 cups. More than 3 are rare here. Here's some data by these people, Shidella and Hatchell, and this is the paper that they had this work in. And so looking at the natural environment, history of the Arctic oil field. So here what they found was the litter sizes 11% single cub, 50% 2-liter cub, and 39% 3-liter cubs. Well, the mean and variance of this. And also what's given to us is that a viable population of grizzly bears, the number of cubs should be not lower than 2. We want to decide if this particular population of grizzly bears is viable. So the first thing to do is define ourselves a random variable that's appropriate, and then determine distribution. So here my random variable x denotes the number of cubs in a litter, and then distribution here is next slide. Now I've changed this a little bit. I've actually got, from the data itself, I've got all the way till 5. The data given in the question only goes up to 3, but I've given the extra data up to 5 here. So here I want the mean of the number of cubs per liter. So it's going to be again the value of random variable times probability, and add them all up. And I've done the calculations: 1 times 0.1, 2 times 0.47, 3 times 0.39, 4 times 0.02, 5 times 0.01. The mean comes to 2.35 cubs. To work out the variance, I'm using the formula we saw a little while earlier. It's going to be e of x squared first, and the mean squared taken away from it. So I just found the mean over here. E of x squared means the same process, but I now square the values. Square, 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 and times probabilities and add them up. I get, in this case, 6.07. And the variance is going to be this e of x squared, 6.07, minus the mean, 2.35 all squared. And that comes to 0.5475. And the standard deviation is the square root 0.7399. Next question here is this particular population of grizzly bears viable? Because the question says we need the number of cubs should not be lower than 2. Well, here the average number of cubs is 2.35, and also probability of less than 2 cubs is 0.11 only. So this is a very viable colony of grizzly bears. Here's a hard example for you to try yourselves. We'll try this in class together.